You are currently in the Jasmine Ballroom for the session ThunderStrike 2 Sith Strike with Trammell Hudson and Zhao Kaval.
Should have told him my name.
Yeah. So today we're talking about ThunderStrike 2, which is a firmware worm for MacBooks. I'm Trammell Hudson. I really like to take things apart and understand how they work. I'm most famous for some work I've done on reverse engineering camera firmware, specifically the Magic Lantern project for Canon SLRs. I also enjoy retro computing and looking for Easter eggs in old ROMs and things like that. This project got started about 2 years ago when I was looking into helping my firm deploy MacBooks across the company. And we had heard some reports about rootkits, so I was asked to use my reverse engineering skills to look into that.
So I'm Zino Kova. Unfortunately, Corey couldn't be here today. We've been active in the firmware security area for the last couple of years, specifically PC firmware security. Corey and I just founded LeguaCore this past January, and we're basically the only company right now which focuses exclusively on PC firmware, peripheral firmware associated with x86 systems, and all of that.
So this talk has its start last year at CCC. I presented ThunderStrike, I suppose now ThunderStrike 1, which was the first firmware rootkits for MacBooks. And the day before my talk, Rafal and Corey presented attacks on UEFI security that included quite a few really interesting vulnerabilities in Windows and Linux systems. After the conference, we got to discussing could we team up and try porting some of those Windows and Linux vulnerabilities over to the Macintosh and find out if they were actually vulnerable. And it turns out that they are. And that's actually one of the main points of this talk, is that EFI systems and UEFI systems share lots of common code. And because of that, they have a lot of common vulnerabilities. So let's jump straight to a quick demo of our proof of concept. So unlike ThunderStrike 1, ThunderStrike 2 has the ability to get started from a pure software environment. So in this case, we're using a root exploit to elevate privilege from some sort of remote code execution to root. We're then able to install a whitelisted kernel module that gives us access to all of main memory. We can then memory map the SPI flash registers, and on some Macintosh systems, we're able to immediately unlock and write to the flash. This builds on the ThunderStrike 1 research, in which we reverse engineered how Apple is protecting the integrity of their ROMs with CRCs, as well as the structure of their firmware volumes. So here we have appended our payload to some empty space in the firmware and updated the CRCs. The other thing that the proof of concept does is it will search the PCIe tree and look for removable devices that contain something called option ROMs. And then it writes its proof of concept to those option ROMs as well. Specifically, we are looking at the removable devices, such as the gigabit Ethernet adapter that plugs into the Thunderbolt port. So in this case, the proof of concept has now transitioned from that software, the software running on the system, into the ROM in that adapter. We are deliberately not being at all stealthy with ThunderStrike 2. So when the system reboots, we'll see the logo come up. And this is being executed from the boot flash on the motherboard and is controlling the system from the very first instruction that it executes upon boot up. So one of the exciting parts about this sort of worm is that we can bring in a fresh, clean laptop and share that Thunderbolt adapter with it. And when it boots, it will load and execute the option ROM containing the payload out of that adapter. this doesn't control the system from the first instruction, so the firmware has already locked the BIOS so that we can't write to the boot flash. But what we can do is leverage the attack that Corey and Rafal had described by hooking the S3 resume script. And the option ROM then allows the system to boot normally. And at some point later, when the system goes to sleep, the CPU shuts off as part of the S3 suspend to RAM. What Corey and Rafal had identified is that in this state, all of the flash protection bits are unlocked, and there's a window of opportunity on some systems before the S3, there's a window of opportunity that when the S3 script is executed, that it can write to the flash. So in this case, we've written to the boot flash, and this is now independent of the OS. You could reinstall OS 10, and it's still there. You could swap out the hard drive, it's still there. This is literally controls the system from that first instruction. So again, we're not trying to be stealthy, so when the system reboots, we'll see the logo again. A weaponized version could use SMM or virtualization, such as the blue pill, to hide from attempts to detect it. So the proof of concept is also watching the PCIe bus for fresh devices to be plugged in. So when a clean Thunderbolt adapter is plugged in, it detects that event and writes the proof of concept to it. So this adapter can now be removed, and as it is shared between systems, it can spread, potentially crossing air-gap security measures. So what we've shown here with this proof of concept is a unique life cycle that starts as a software exploit that's able to write into the boot flash of some systems, that can then write into the option ROMs of removable devices, that are able to infect the S3 resume script on new systems and write into the boot ROM on those.
Right, so this is, again, the main point of the talk is the fact that all systems potentially have vulnerabilities that are shared amongst them because there's this common UEFI or EFI base. So just a very brief history of EFI. Basically, when Intel was trying to make their non-backwards compatible IA64 architecture, they said, we don't want to keep using this old legacy BIOS cruft. We want to create something that's more modular, more extensible, and we're going to use that for our new architecture. So they started the extensible firmware interface that way. Apple, when they moved over from PowerPC chips to x86 chips, they adopted Intel's preferred implementation of the firmware. So Intel tried to bring more people into the fold and create the unified extensible firmware interface forum, and this was sort of an industry consortium of many vendors that all sort of contributed to UEFI and sort of oversaw its progress going forward. So still, even though Apple had forked off here some point before UEFI was even formed, there's still millions of lines of code, right? They didn't create UEFI and then just rewrite the whole thing from scratch. It's just an evolution of EFI. So the way that firmware typically works today is that you have the open source UEFI reference implementation called EDK2, EFI Developers Kit 2. And that's open, that's public, but then independent BIOS vendors will typically fork that, add additional features, and add their value to it. And then they'll sell it to OEMs in order to make their machines that they sell to you. So basically, because of this hierarchical structure where there's the open source reference implementation, and then there's some vendors that add their own competing features, and then there's all of the OEMs who buy from them or maybe fork off their own way, that means that just because a vulnerability gets fixed in the top of the tree doesn't mean that it gets fixed everywhere, and doesn't mean that it trickles down to everyone. Right? So one of the points of this talk is to show, no one's special, no one's immune to this kind of thing. When you go down and look at firmware down at the lowest level, throw it into IDA the way an attacker would, you see that there are dramatic similarities, and that means from attacker's perspective, consequently, they don't really have to do that much different in order to attack a Mac versus a PC. So this is just an example. There's a random ASUS machine that we used for our CanSec West talk this year. So we analyzed it, we annotated it, there's comments on it. But if you go ahead and look at the MacBook Air, which we threw into IDA without any special annotations, everything pretty much looks the same. We've got the same control flow structures. We've got the same code being called in the same order, the exact same functions, same registers showing up in some places. And so it's just overwhelmingly, there are places of similarity that can be leveraged by attackers. So there's these shared vulnerabilities, there's this shared code, and what we see are situations where vendors are not necessarily using all the protection mechanisms that are available to them. And furthermore, we've still got some legacy decisions around things like option ROMs that mean that there are still these sort of avenues, very old avenues for attack within systems. So we're going to consider sort of 4 core vulnerabilities that are all sort of old news. These are all vulnerabilities that have been found, responsibly disclosed, publicly disclosed, and acted upon by other vendors. But when we looked at these all still applied to Macs because Apple hadn't dealt with them when we started this research. So the first thing to consider is the speed racer vulnerability. This is a fundamental hardware vulnerability. It's a race condition in the hardware and the way the hardware behaves, and consequently you would expect that anyone using vulnerable Intel CPUs are going to potentially be vulnerable to this bug. So I have to explain just a little bit. This is just going to be a very brief summary of each of these 4 issues that have been previously fully publicly disclosed, and you should see the past talks for full details. So the core oldest protection mechanism for BIOS was the interaction between the BIOS write enable bit and the BIOS lock enable bit. If you want to write to the BIOS, you need to set BIOS write enable equal to 1. If the system wants to protect itself, it wants the system to be writable at the boot time, but then they at some point want to lock it down and say no more. No one in the operating system should be able to write to the BIOS. So in that case, they would set the BIOS lock enable bit. And this is not a hard lock. This is not a forevermore no one else is allowed to write to the BIOS until we reboot. This is a soft lock where once that bit is set, anyone who comes along and tries to set BIOS write enable equal to 1, they will cause a system management interrupt, and any code that the firmware has set up to catch these system management interrupts will get to make the access control decision and decide, should I allow this person who's trying to write to the BIOS to actually write to the BIOS. And so this previous mechanism, this oldest mechanism, this works great when you have single-threaded, single-core CPUs, which is where it was originally introduced. But what we found was that once you move over to systems, even if it's not multi-core, we found that even a system that's just hyper-threaded, this core race condition can actually happen. So the race condition is, we have a situation where one thread of the hardware can continuously say, I want to set BIOS write enable equal to 1. So set it writable, set it writable, set it writable. The other thread will continuously say, write to this address in the BIOS, write to this address in the BIOS, write to this address in the BIOS. And you've got these 2 threads just hammering on these bits. Every time the first thread sets BIOS write enable equal to 1, then the system management interrupt will fire. All the CPUs have to get into system management mode. System management mode needs to run some code, decide whether or not it wants to allow the system to write there. And while all of that other activity is happening, sometimes you have a situation where BIOS write enable is equal to 1, and then the other thread slips through a write to the BIOS. So that's the core race condition. This was disclosed to Intel in May of 2014, and it was publicly talked about by Corey at CCC in December of 2014. So we told Intel about this, and Intel said, yeah, we know that can potentially be an issue, but that's why we introduced this additional bit, this SMM BWP bit. That was introduced around 2004 or so when Intel moved over to the platform controller hub. So any hardware that's older than 2004, that's just going to be vulnerable forever, pretty much. And any newer hardware, that's going to have the option to set this bit, but it's incumbent upon the BIOS makers to actually set that bit. So the SMM BWP bit says, I'm going to layer additional protection on top of that. Even if someone successfully sets BIOS write enable equal to 1, I still want to disallow them access to the BIOS unless the processor is currently in system management mode. So that means our attacker just hammering on the bits behind the scenes. They're a kernel level attacker. They haven't necessarily found a way to break into system management mode, and so they would be prevented from being able to write to the flash chip by this bit. So this is the way that Intel recommends the protection bits be set. You've got this layering where, the first more coarse grain sort of access control decisions are if the BIOS lock enable bit is set, if someone tries to set BIOS write enable, then SMM can decide if they're going to allow it. Then there's the other bit, SMM BWP, that says, okay, only the BIOS only the CPU while it's in system management mode will be allowed to write to the BIOS. And then there's these further bits, the protected range registers, which a vendor can use to create non-contiguous places where the firmware is actually protected even from system management mode. So even if someone were to break into system management mode on properly configured systems, they're not going to actually be able to write into the flash chip. So that's the way Intel recommends that it be set. So for all of our previous vulnerabilities, we disclosed them through CERT and the UEFI security response team once they were stood up. We like to use CERT rather than CVEs because CVEs just says, okay, here's some vendor advisory, something like that. The nice thing about CERT disclosures is it shows here's the people who said yes, we were affected, and hopefully there's a link there to the fixes for it. Here's the vendors that said we are not affected, and here's the vendors who just didn't say anything. So, right, Apple said they're not affected by this. And there's no penalty for being wrong, right? A vendor can say, nope, not my problem, prove it, right? Show me the money. So a vendor can say, I'm not vulnerable, and that may or may not be true, and it becomes incumbent upon researchers to actually go and find out, is that actually the case or not? And of course, there's all these sort of vendors down here which, they don't say anything, and you can pretty much guarantee that the vendors which don't care enough to even respond to a vulnerability disclosure, they're probably vulnerable, right? So, right, incumbent upon us, is Apple vulnerable to Speed Racer? Well, if you check the bits, you see that BIOS control is set to 8, which means that the BIOS lock enable bit is not set, the SMM BWP is not set. So in a technically correct sense of the word, they are not vulnerable to Speed Racer because you don't need to use an exploit to get around a protection that was never there in the first place. Right? So this is what the protection looks like on a brand new Mac Mini, which I purchased. And so we've got those first two layers are simply not there in terms of protection. So you've got this protected range registers, which is good because it stops an SMM attacker, but you've got these two gaps. So a kernel level attacker can go ahead and just write into these gaps. There's the EFI variables. These are the things which you would normally edit from the command line with the NVRAM command on a Mac OS X system. But there are even some variables which NVRAM will not allow you to access. But because the way this protection is set up, an attacker could just go in here and set anything they want, right? But then there's this very interesting other region, which we don't know what's even in there. And we just said, okay, well, I'm going to smash the variables. I'm going to smash the padding.
Yeah, we don't know what's going on either.
Oh, that's interesting. Oh, I must have hit down magic. Clear the screen button. All right, so basically there's a gap with, there's a gap for the variables, right? Because they essentially, what that implies is they want runtime accessibility of those variables. And then there's some other gap with some other stuff, which we don't even know what it is. The UEFI tool just says it's padding. It doesn't know what it is. And what we ultimately found was that if you write into that first gap, then the system will become corrupted and the system will never boot again. So that's a trivial way to brick a brand new system with all of its, with all of the default protections set. And so Apple systems out of the box, vulnerable to being bricked. So we'd show you a demo video for this. There is a demo video for this. You can go watch it later, but demo video screenshot, not super interesting. The computer just doesn't boot anymore, right? So it's hard to make that exciting, sorry. So there's still these protected range registers that an attacker would have to get around if they wanted to do something useful, right? Bricking the system is all well and good, and that can be a very severe attack to recover from. But an attacker would usually like to take stealthy control of a system rather than just turn it off, right? Unless you're whoever attacked Saudi Aramco. So there's the Darth Venomous vulnerability. sometimes referred to the Dark Jedi attack. This was named by Rafal because in the Star Wars universe, Darth Plagueis defeated his nemesis, Darth Venamis. He killed him, and then he kept resurrecting him, putting him back to sleep, killing him again, resurrecting him, putting him back to sleep. So through this continuous process of killing and resuming, he learned the science of midi-chlorians, right? So use killing people to learn about science. So this is exactly what the Darth Venamis does. It uses this built-in capability called S3 Sleep, ACPI. S3 Sleep, whenever you close the lid on your laptop and it goes to sleep and then you have this ability to quickly wake up again, that's an S3 Sleep. You're going into a low power mode on the processor, and that leads to, unfortunately, some access control bits coming unset. So this core vulnerability was disclosed to CERT and the UEFI security response team in September of 2014, also independently discovered by the Intel Advanced Threat Research team. And this was publicly disclosed by Rafal at CCC in December of this past year. So just a very brief sort of overview of what they covered in that full hour talk, which I recommend you watch. The basic process, you boot up your system, and as you're booting the system, you have the full code, which is going to, the whole point of firmware code is to configure the system, set the hardware into sane configuration so that you can run a full-fledged operating system, right? So that's a relatively long process, and what you want with this S3 Sleep is you want the ability to close the lid and then open it up and have it resume extremely quickly. So as the boot is going through a normal boot, it's going to save off this little cheat sheet of like, what is the minimal configuration that I need to do to get the system back into a basic configuration where it's fully functional. And that cheat sheet is the S3 boot resume script or resume script. And so on the top column, on the top row, that's the normal boot process where you save off your script of what you're going to execute when you wake back up. And on the bottom row, upon resume, you basically just walk through and you execute each of these opcodes within a script. And the opcodes do basic activities like writing to memory, reading from memory, writing via port I/O, reading via port I/O. But there's a big kicker in here, and that is the dispatch opcode. So amongst this little script of do this, then do that, and do that, and do that, there's a little caveat, there's a catch-all, which is the dispatch opcode that says, whatever I need to do to reconfigure the hardware, it's too complicated for me to do with just simple reads and writes of memory. Just jump to some arbitrary code, and that code will execute and do whatever it needs to do. So what the core finding of Darth Venamis attack was, if you find those sort of dispatch opcodes, you can overwrite them and force the system to jump to attacker-controlled code. What that means is that ultimately, with Darth Venamis, all of the protected range registers can be made to go away. So you go down into a low power state, all of the hardware loses all of its configuration bits, you wake back up, and now the system is completely open and vulnerable to writing. So now an attacker can go after the code and stuff. So Darth Venamis, this was an interesting sort of situation where when we looked back to see, did Apple say they were vulnerable? Did Apple say they were not vulnerable? You look at the CERT disclosure for this, and whereas normally CERT would say who didn't say anything or who said they were not vulnerable. In this case, all it said was some vendors that said they were affected and potentially had patches. So with a little bit of digging, we found that it turned out that CERT actually dropped the ball on this one. CERT didn't disclose this to Apple explicitly. But as I said, we disclosed this also through the newly formed UEFI security response team, which was stood up because of all the various attacks that have been happening over the past couple of years. They said, we need a good way to get out this information to all of the members of the UEFI forum. And given the fact that Apple is a board-level member of the UEFI forum, you would expect them to listen to their own security response team. So Tramel's previous vulnerabilities with ThunderStrike, it was the first time anyone had actually showed the ability to reflash the Mac. Previously, from Snare's work, there was a question about whether or not there was some special protection that Apple is doing with hardware to prevent writing to the flash chip. Tremel showed no, Apple's not doing anything special. You can just go ahead and write to the flash chip if you know the right way to fix up the CRCs and everything. Furthermore, once you combine Darth Venamis with this, there's no longer any sort of requirement for physical access to attack firmware, right? So ThunderStrike 1, physical access. You had, little Thunderbolt Ethernet adapter. Darth Venomous, now an attacker can put the system to sleep, wake it up, and write to the flash chip. So the way that generally works is that if you look at the system, you look at a system as it's just normally running, and yes, you will see the protected range registers properly stopping an attacker from writing into the flash chip. But because of this resume script issue, the resume script is stored in unprotected memory. Forgot to say that. Right? The resume script is just sitting around in RAM somewhere. So an attacker can come in, modify the resume script in that dispatch opcode, that place where it jumps to arbitrary code. They rewrite that. They point it at some temporary space. They insert some code to the temporary space. In this case, the proof of concept just sets a lock bit in the flash lockdown register. So literally just a couple of instructions, writes the lock bit, and this means we went down into when we go down into sleep and when we come back up, the system will be prematurely locked, and the normal boot script will not be able to write and turn on those protected range registers because it was locked before the rest of the code had a chance to try to set it. So go to sleep, just use a power command, go to sleep, wake back up, and now the system completely unprotected, and consequently, we just disabled protected range registers. Apple doesn't use BIOS lock enable, Apple doesn't use SMM BWP, so that means it's game over and anyone can write anything, anywhere into the flash. We just wrote hello world into the flash because we knew we could do that and it wouldn't break the system. So you may have heard of a related vulnerability called Prince harming. We had found actually this same sort of vulnerability a while back in our research. In 2013, we found this vulnerability, we disclosed it, and it got fixed. And it took an inordinate amount of time to actually post this vulnerability posting because they said, well, it's already fixed, we don't need to coordinate it. So we had to wait for this vulnerability to come along and say, okay, well now it's not fixed, yet another vendor has had this problem. So then they decided they would coordinate this and post our thing we gave them back in 2013. So the Prince harming vulnerability was found by Pedro Valaca, and he didn't want to give it any particular name, but Katie Moe came along and said, let's call it Prince harming because, Prince harming wakes you up with the poison kiss, and it's all very sketchy. You've got this vulnerability thanks to the poison kiss of Prince harming. So back in May, Pedro posted a blog post, and in the post he talked about how he had seen the title of this talk. He had correctly inferred from the Sith strike that this talk would have something to do with Darth Venomous, and he said he had been looking into Darth Venomous and its potential applicability to apples. But he said that while he was doing his research, he found a much more severe vulnerability that he didn't have to manipulate the boot script whatsoever. He just put the system to sleep, woke it back up, and it was, for whatever reason, not actually setting the protection bits. So they were forgetting to set the protection bits when it woke back up. And as you can see, this was a cause for concern, and it left much to be desired. So the Prince harming vulnerability was publicly disclosed back in, in his blog post in May. He assumed incorrectly that we had already seen Prince harming and disclosed it to Apple. He assumed that, so. We had previously been testing our systems and testing for vulnerabilities of previously disclosed vulnerabilities on MacBook Pro 11.2s. So these are newer systems, and these do not exhibit Prince harming. So you put it to sleep, you wake it back up, and it is not actually vulnerable. It's still correctly set. Pedro had actually been testing on MacBook Pro 10.1, and on that system, you put it to sleep, wake it up. So our systems were vulnerable to Venomous, so you could manipulate the boot script and things like that, but they were not vulnerable to Prince harming. So basically, Apple either silently or accidentally fixed the problem in the newer machines, and then they didn't backport it to previous systems. And so consequently, Pedro basically accidentally put out a firmware level 0 day, like, dear everybody, put your Mac to sleep, wake it up, and you can go ahead and write into the flash chip and backdoor the system. So, oops. Right, but after that firmware 0 day was out there, Apple turned around a patch relatively quickly, and this EFI Security Update 2015-01, this fixed Prince harming, and it partially fixed Venomous, Darth Venomous attack. So if you look at the update, you'll see that it basically applies to everything from 2011 and forward. So 24 different models were actually fixed. But when Tremel took a look at the patch, he found that there were some potential issues with it still. So it said it improved the locking on the system, but what does that actually mean?
So I pulled down the firmware update and did some diffs between the different versions, and found that Apple is now setting the protected range registers and locking them in PEI before the S3 boot script is executed. And this is the right place to do it, and it does prevent writing to the boot flash as we showed in our demo. However, the BIOS control bits are still unlocked, so it's still possible to break the system. The S3 boot script is still unprotected, so you can do all sorts of interesting stuff in there. And the TSEG MB register is unlocked. This is yet another legacy feature that potentially allows a device to DMA into SMRAM, which allows it to get code execution in SMM. The other thing I found is that there appears to be another silent fix, that the latest MacBook, the USB-C one, protects the S3 boot script via some mechanism. So it's not subject to the Darth Venomous attack, but all of the previous models still are. So another legacy feature that ThunderStrike 2 uses is option ROMs. ThunderStrike 1 also took advantage of this. And this goes back to the earliest days of the IBM PC. Where the BIOS was typically socketed, and there were spare sockets on the motherboard for optional features, like the basic interpreter or a hard drive controller. Expansion cards, like video cards, were also allowed to have expansion ROMs on them so that the BIOS could write the early boot messages out to those displays. Using this as an attack vector is not really a new idea. John Heisman presented at Black Hat 2007 with the proof of concept that executed from PCIe cards in desktop and server systems. And in 2012, Snare streamlined that and showed how to implement a option ROM in a gigabit Ethernet adapter that could backdoor the OS X kernel. His talk was the one that actually started me on this project a few years ago. Intel realized that option ROMs posed a problem for secure boot, and as part of the secure boot project, required that expansion cards had to contain cryptographically signed option ROMs. This was merged into UEFI 2.3 and again required for secure boot. As we mentioned, though, Apple is basically frozen on the older EFI 1.10, and they are still unconditionally loading and executing option ROMs from both internal and external devices on the Thunderbolt bus. And this is despite Heisman's talk in 2007, Snare's demo in 2012, and then my ThunderStrike demo in 2014. And it really needs an architectural fix, that there needs to be a way to either whitelist ROMs, to disable ROMs if they're not necessary, or in many ways to be able to trust the contents of them. The ThunderStrike 1 talk also hypothesized that these removable Thunderbolt devices could be used to virally spread this sort of attack. At the time, the only way to write to the ROMs was to reboot to DOS and have physical control of the adapters. And that's kind of messy and not very streamlined. So what we figured out, though, is that the Linux Broadcom B57.C kernel driver has support for reading and writing the option ROMs. So we were able to port that over to OS X, and now you only need root access to be able to map the PCIe space in order to write to them. This also works from DXE or PEI mode, since they have access to raw memory. This means that now an attacker who can get a root shell on the machine using whatever attack is currently unpatched is able to install the whitelisted direct hardware kernel extension, map the PCIe space, and then write their code into the option ROMs of those devices. We most of these demos are using the Thunderbolt devices because they're very convenient, they're removable, and fairly inexpensive. But there are lots of devices in the system that potentially could contain option ROMs. There are some models of Wi-Fi cards, some GPUs, and some SATA controllers in the internal SSDs that have option ROMs as well. So even if you can't get persistence into the boot flash, you can still sometimes get persistence into the peripherals, which is almost as good, because this does run before the kernel starts and gives you the ability to do quite a bit of backdooring.
All right, so one last time for good measure, right? UEFI vulnerability is shared amongst many systems. Just because a researcher doesn't say it applies to one particular model or your particular model, your particular machine, does not mean that it does not apply to your particular machine, right? It's really just a question of motivation and effort in terms of looking into these kind of things. So ultimately, we basically did this survey of multiple public vulnerabilities that we'd already disclosed, and here's the net result of it. Snorlax or Prince Harming, that was fully patched by the June 2013. So no longer, if you go out and apply the BIOS updates, which we always harp on, go apply your BIOS updates. If you go out and apply the update, then if you put it to sleep and wake it back up, it will not just be vulnerable by default. It'll still be partially vulnerable to Darth Venomous. The attacker could use that to break into SMM and live in RAM that your memory forensics can never take a look at. But, and the other things that Trem will mention. And there's also the Speed Racer issue, which, as I said, it's kind of, they're not vulnerable to the hardware. I mean, their hardware is vulnerable to the hardware race condition. They're supposed to be setting SMM BWP in order to have the system properly protected, but they're simply not even using that protection bit. And then, interestingly, King's Gambit, Corey's vulnerability, which he just won a pony for yesterday, and which I talked about, we both talked about here at Black Hat last year. That same vulnerability is actually still unpatched. So although Apple patched the vulnerability, so Darth Venomous, as the proof of concept video will not work directly. King's Gambit gives us the exact same capability without the need for a sleep and resume. Gives us the ability to write into the flash chip and fully take control of the system. So that's still unpatched. Apple's working on a patch for that, but you can hear Corey talk a little bit more about that at the upcoming Hack in the Box GSEC conference. The Sicilian was another one of Corey's vulnerabilities, disclosed at Eco Party in 2013. That was a situation where we were trying to make the point that Invisible Things Labs in the past had said, just because you break into SMM doesn't mean you can break into BIOS. And we were trying to show, yes, in some cases, if you break into BIOS, you can break into, if you break into SMM, you can break into BIOS. The sixth thing that we did consider, which is not at all applicable to Apple systems, is the setup vulnerabilities, which had been found by Intel and ourselves. There's a variable which is very common on many UEFI systems. A lot of PCs have it. The setup variable, if corrupted, will lead to bricking your system, and if manipulated, will lead to breaking secure boot. So this has been a widespread vulnerability, but does not apply to Apple's because they just simply don't use this, because they just simply don't do secure boot. And there's no equivalent sort of thing. So, what can vendors do to actually improve things? Because, I know you're all BIOS vendors out there, so let me lay some truth on you. Testing vulnerabilities from other systems, if they're in the BIOS and firmware world whatsoever, you need to check whether those actually apply to you. Right? Silently fixing vulnerabilities, bad karma there. Using all the lock mechanisms that the vendors provide you. If Intel says, here's all these lock mechanisms that you can use, it probably behooves you to use them. You can maybe get away with using less protection mechanisms, and then, it's that much less work for an attacker to eventually break into the BIOS. ChipSec, Intel's tool for checking BIOS vulnerabilities, can be used to just sort of automatically determine whether a given system is patched or not. If you're using Windows or Linux, you can just go use ChipSec. ChipSec doesn't support Mac OS, so if you install Windows on your Mac and then you go run ChipSec there, you will see it telling you, all right, this system is vulnerable because it's not using all the protection mechanisms. There are other things like SMM Lockbox, which helps lock away the S3 boot script so that it can't be just sitting around in RAM for an attacker to manipulate. That's actually used in the EFI open source reference implementation, but we actually see very few vendors which actually use the lockbox. And beyond that, the lockbox is not a panacea in and of itself, because they showed in the Darth Anonymous attack that in some cases vendors misimplement the lockbox, and then it's still vulnerable. On newer systems, Intel has a technology called BootGuard, and BootGuard provides a much stronger root of trust for the system so that you know that the system does not execute the very first instruction out of this flash chip, which an attacker can potentially reprogram and take control of. It executes it out of some signed code that Intel provides, that the signature, the public key is built into the CPU itself, and so the CPU actually validates the digital signature on that code. And of course, option ROMs, this has been sort of a long-running problem. This ability to, backdoor the system to compromise the kernel, which is obviously what, at the end of the day, a lot of things the attacker wants to do, maybe get into the kernel. It's just been a long-running problem, and there needs to be additional security around that. All right, so for the rest of you who are not BIOS vendors, right, what can you do? Well, you need to start doing firmware forensics, right? It's not just about hard drive forensics anymore. It's not just about memory forensics. Your firmware and all of those little firmwares scattered about your system, they need actual checking, right? That's part of the reason why we started our company, is because we didn't see people actually checking their firmware. So we work with vendors in order to remove vulnerabilities from firmware, but if there are vulnerabilities out there in unpatched things, then you could still get infected, and you need a way to actually check that. So we are putting out a basic tool, basic Band-Aid. What can you do in order to check whether or not you've got ThunderStrike 2 firmworms running around on your network? Trammell's going to be releasing the source for his option ROM dumping tool, sort of ported over from Linux to Mac, so that Mac users can just natively dump the option ROM off their Thunderbolt adapters and consequently take a look at it. And we're releasing a script, it's already posted, which you can use to go integrity check the firmware in order to see, is there anything modified about this firmware? Is there any code injected into it? It's actually, pretty easy to integrity check the firmware, so consequently just simple script, bam, 0 or 1, has it been manipulated or not? Now, there might be some false positives because we've only checked it on, our few Thunderbolt devices. So if you go off and run it and it says, there's an unexpected change to your Thunderbolt Ethernet adapter, well, it may be a false positive or it may be a true positive. Let us know in either case. Also, what can you do? You can go get smart on security for free from Open Security Training. Go learn more about rootkits and what they can do to you.
So thanks for attending our talk. We will have some further information as well as an annotated transcript up on our different websites. You can see how to contact us. And please be sure to fill out your evaluation forms.
And that's it.
Thank you.